All right, turns out that there's a different way of writing this stuff that is also useful. I'm going to claim that if we define zeta as we have before, zeta is equal to c over 2 root km. And if we define omega n is equal to square root of k over m, then I claim that we can write the amplitude as f naught over k square root, or times 1 over the square root of 1 minus omega over omega n, that squared, all that squared, plus 2 zeta omega over omega n, all of this also squared. So kind of complicated. Let's show it. What we need to do is substitute in for zeta and omega n, and we'll see what happens. Okay? So let's see if that's correct. That's equal to f naught over k 1 over square root of 1 minus omega over root k over root m, all that squared, right? So let's just make this an omega squared and make this a k over m. All that is going to be squared. Plus 2 times zeta. Zeta is c over 2 root km. And omega over, let's see, root k over root m. All of this is going to be squared. Let's go ahead and simplify things while we can. Looks like we're going to have the k's multiply together. Excuse me, this 2 is going to cancel out with that 2, so let's go ahead and get that out of the way. Let's go ahead and take the k's and multiply those together. So this becomes k times root m, and this becomes 1 over root m. We can get rid of those. That becomes 1 over there. So this simplifies quite a bit. It becomes c omega over k. Okay. All right. Excuse me. All right, so let's go ahead and multiply. Actually, well, I'm going to do this in place here. All right. This k here can come inside the square root. Let's go ahead and bring it inside the square root. Let's put this f naught over here. Give us a little bit more room to bring that inside the square root. That means that everything here is going to get multiplied by k squared. K becomes k squared inside the square root. So we're going to distribute it. It's going to become k squared times the first term plus k squared times the second term. Let's shorten this. Okay. Let's go ahead and bring this inside this term. Well, it becomes k times inside there. We brought it into a square. Okay, so we need to multiply that through. This is going to become k, and this becomes 1 over m, which we can go ahead and just make that m omega squared. And that also can go inside, and it gets rid of it. And now we have a very jumbled form of f naught over the square root of k minus m omega squared plus c omega, that quantity squared. Let's go ahead and find out what the phase is. The phase is phi is equal to, I claim, the arctangent of 2 zeta omega over omega n over this 1 minus omega over omega n. That quantity is going to be squared. That's what I claim. Let's see if it's right. Okay, let's go ahead and simplify by plugging things in. Let's just go ahead and work on this expression. Forget about the arctangent. Let's go ahead and simplify this. That becomes 2 times c over 2 times omega over root k over root m. And that is all over 1 minus omega over root k over root m. That quantity is squared. So let's go ahead and simplify things. These 2's cancel out. Cool. This square root of m divides out that square root of m, becomes 1. These k's can combine, become a full-fledged k. On the bottom here, we have, let's just square both things, so omega squared, this becomes k over m. Well, this k, let's bring it down on the bottom, k c omega on top. So let's multiply everything through. Well, actually, let's bring this m over here first, m omega squared. And this k gets multiplied through. Get rid of that. And we've simplified the argument of that function into what we had before, c omega over k minus m omega squared. Cool. Now, the last thing that we do is we often define a quantity. I'm going to call it R, and it's omega over omega n. I call it the frequency ratio. And so when we write this, just because omega over omega n appears so much, it becomes a little bit more convenient if we write this as R squared. We can get rid of that crazy bracket there. Just make it a regular old parentheses. That can be squared. And this becomes 2 zeta R, that quantity squared. Likewise, we can go ahead and make this 2 zeta R. And this becomes 1 minus R squared. And so these are sometimes convenient ways of writing our amplitude and the phase. And finally, it's also nice to define a quantity, this thing here. I'm going to call it alpha. This is the amplitude ratio. Now we can just write out, so this whole thing, this whole quantity, 1 over the square root of 1 minus r squared, that squared, plus 2 zeta r, and that squared. We call that the amplitude ratio, and that makes it easy to write. The amplitude is just f naught over k times the amplitude ratio. And so we can kind of think of the amplitude f naught over k. What does that signify? F naught over k. Well, first of all, alpha is a dimensionless number. So this is going to have the right units, f naught over k. Oh, yeah, that's right. This is a force over a stiffness. Stiffness is force per displacement. So this becomes a displacement. So our amplitude is in units of displacement. That makes sense. F naught over k, well, that's kind of like the force F naught over k, the force, if this were a constant force, if we had a constant force F naught acting on the mass, F naught over k, that would indeed be the amplitude, the displacement, right? That would be the displacement. And so we're going to get the displacement, if it weren't like a sinusoidal force, for a constant force, times some amplitude ratio, alpha.